Hello everybody, we're going to go over special examples of IMFs and bulk solids in this lecture. There are just going to be a few random special examples that you will have to memorize because they're pretty important to biology, and since you've learned about these things previously in your biology class, we like to come back to them and point out a little bit more of the chemistry that's involved. And it'll probably make a little bit more sense now that you've learned about IMFs. We'll also learn about these things called bulk solids, which are a little bit strange because they're kind of a combination of inter and intramolecular forces. So we'll kind of see what happens when you start putting all these together. You get something called a bulk solid. So the first example of special IMFs we have is for hydrogen bonding. DNA is super important example of hydrogen bonding because DNA has this alpha helix shape. You learn about that in biology. It's a spiral and it has base pairs that match up like little puzzle pieces. Usually they show it in a very cartoonish way, and they kind of imply that they're puzzle pieces that they have to notch together somehow, and that they tell you only certain combinations can work. They usually teach you that hydrogen bonding is occurring at these base pairs, but they don't always tell you exactly why that's so important. If these base pairs were covalently bonded to each other, they would not come apart easily. If you remember, DNA has to unzip in order to be replicated. And so if they're covalently bound, getting those two sections to unzip would be very difficult. If they were ionically bonded, that would not be very good because we're mostly water-based, right? And ionic bonds come apart in water most of the time. So that probably wouldn't be a good idea either. So the solution to this is to use hydrogen bonds. A hydrogen bond won't be as strong as a covalent bond, but it'll be strong enough to keep that DNA spiral together until it needs to unzip. It'll be much easier to take apart if it's not a covalent bond. So I like to use the example of glue is the covalent bond and Velcro is the hydrogen bond. You can take Velcro apart and put it back together much easier than if something was glued together. They're both ways of attaching things, but the hydrogen bond is going to be much more functional because it's much easier to break apart than that covalent bond. You should have a small little glue-in for your notes that shows you the base pairs. Sometimes in your biology class, they don't show you what these actual base pairs look like. So I'm going to show you kind of the important parts of this base pair. So here's the A and T pair, and here's the G and C pair. You may notice over here there's an R, and there's an R, right? Here's another R and another R. That's where they're connecting to the rest of the DNA. That's like where they connect to that backbone. So we're just interested in the main portion here of the base pair. If you notice, look here. We have nitrogen and hydrogen and an oxygen. We got a dashed line here. We got another dashed line here. There are two hydrogen bonds here. And on this side, you can see, look, there's 3 hydrogen bonds. The reason the A and the T have to pair together is because that's the only combination where their hydrogen bonds will align. The G and the C have to go together because that's the only combo where all 3 of those hydrogen bonds will line up properly. So that's why we have to have those combos. So on your little glue-in, just go through and highlight where those hydrogen bonds are. I would never ever expect you to know what the base pairs look like. I would not expect you to try to look around and find where all these hydrogen bonds are occurring, but I do expect that you know enough to understand that the dashed lines are your hydrogen bonds, and that you could be given something like this and you could highlight where they're taking place. So that is the kind of thing I would ask you to do. If you did not print your glue in yet, don't worry about it. You can come back and do that later. Remember, you can always access the notes from the class website. You can always rewatch the video, so not a problem. All right, the next special example of IMFs, of hydrogen bonding, are proteins. So kind of similar to the DNA, remember we can have these interesting structures. So you can have the alpha helix like DNA. You can see here, it starts being held together in all these different directions by hydrogen bonds. You can also get what's called beta sheets, where it folds in a slightly different pattern. But the folding is taking place because of these hydrogen bonds. They're trying to line themselves up, and so it starts to turn into these interesting shapes. You can then have these shapes, these beta sheets and alpha helixes start tangling up on each other. Remember, you have primary structure, secondary structure, tertiary structure, and quaternary structure. The primary structure are the actual atoms connected together. The secondary structure is these helixes and these sheets. And then the tertiary structure is when those start tangling up on each other. And then the quaternary structure, they start tangling up with other proteins, other complicated molecules. So they probably taught you about hemoglobin, and that you had all these very complex foldings and shapes, and they all get tangled up perfectly together so that they can transport iron, so that they have iron on them that can transport oxygen around your body. And so if they don't get folded properly, then it's not going to work. You're going to have problems. So this is all going to work because these hydrogen bonds line up perfectly. So sometimes, there's errors in your genetics that might cause issues with protein folding, and it might make these hydrogen bonds not line up properly. And that's how you can get some, problems. All right, moving on, we're going to learn about bulk solids. So bulk solids is what happens when you start getting an overwhelming combination of things. You're going to start getting a combination of intramolecular and intermolecular forces in a really big scale. And instead of saying a large scale or a big scale, we just use the word bulk. If you were to go to the store and you were going to buy something in bulk, like at Costco, you're buying a lot of it at one time, right? So it's not that we have anything necessarily special happening here, but what we have are huge numbers of things happening, which causes all the properties to be a little bit higher than we would expect, because we have such a sheer volume of things happening. So we tend to break bulk solids into three main types: metallic, ionic lattice, and network covalent. You've already learned about metallic substances way back in first semester. You already learned about ionic way back in first semester. But what we didn't really explain to you is that these substances have these inter and intramolecular bonds going on and forces. And so that's why we get these very high properties. Network covalent are not very common. You are going to have to just memorize a couple of examples. They're covalent molecules, but they have some special properties to them. Next is metallic. With metallic substances, we get metal atoms stacked together on top, bottom, left, right, in all three dimensions. They start packing together, and they're very orderly. And what holds them together, if you remember, is that the electrons detach and they can move around. So we say they have a sea of electrons. They're no longer stuck onto one particular nucleus. They start, buzzing around throughout the entire structure. And so that holds them together much stronger, because you really can't tell where one bond starts and one bond ends. The difference between inter and intra gets a little bit iffy here, and so it causes these to be much stronger. The next one is ionic lattice. Here we have positive ions and negative ions stacked together to form these crystals, front and back, side to side, up and down, all 3 dimensions, very similar to how the metallic structures are. And same thing here, it gets a little bit complicated because you can't really distinguish where the intra-bond and the intermolecular force kind of start and stop. You have so many attractions happening in all 3 dimensions, they end up much stronger than you would expect. The last one is going to be network covalent. So here are the ones that you need to remember. You need to remember diamond and graphite, which are both examples that are carbon. They're just different arrangements of carbon. You need to know silicon dioxide, and then the last one is tungsten. The most common that you're going to come across will be diamond and graphite. Sand is mostly silicon based, so sometimes you may hear people reference sand, but that's really just because it's silicon based. So these are both examples of carbon networks, and you can look at them and see they're totally different, aren't they? The one on the left looks way more tied together. The division between the inter and intra bonds and forces is way more complicated, right? They're going on in all different directions, a lot more forces present. On the right-hand side, you have a lot of bonding happening inside these sheets, and then the sheets are going to have a lot of intermolecular forces holding them near each other. One of these is diamond, one of these is graphite. You probably know that diamond is stronger, and so if it's based on the volume of intra and inter forces, then you could probably guess the one on the left is diamond, and the one on the right is graphite. You are probably used to thinking of graphite from your pencil lead, and a lot of times people will say, but pencil lead is not strong. We break our pencils off all the time, have to sharpen them constantly. And that's true, sort of. When you break your pencil, or when you're writing across your paper, the sheets are coming away from each other because those are not held together very strongly. So that's true. I remember like in middle school, people would always scribble their pencil on their paper and they would rub their finger in it to get the graphite all over their fingers, and then they'd try to do like fingerprints with the pencil lead with that graphite dust. And if you ever felt that, it felt very, very slippery. And that's because the sheets are sliding past each other. And so graphite is actually used in a lot of machinery parts to lubricate the gears so that they don't stick together. And one of the things that's so great about that is that the sheets can slide past each other, but the sheets themselves are so strong they won't break down very easily. So that's really great material to use. So even though we're not used to thinking of our pencil lead as being very strong, it actually is. We're just only looking at the sheets coming apart from each other. We're not looking at the strength of the actual sheets themselves. So it's kind of a neat example for network covalent because you can see even within a network, they can be arranged very differently. All right, next we're going to learn how to rank everything we've learned about, from weakest to strongest. Please know this is a huge generalization. Obviously, there's going to be exceptions, but we can't deal with that, right? You got to remember we are high school level chemistry here. If we start looking at exceptions to this, we're never going to have time to finish the year. So realize if you start looking things up online, you may go down the rabbit hole and get really confused. So make sure that you're just kind of following our general concepts that we're trying to teach you. So the weakest amount of forces present in a substance, the weakest type of substance would be something that only has the London forces. If it's non-polar, covalently bound, with London dispersion forces only, that will be the weakest type. The next strongest would be if it's polar, covalently bound, dipole, a little bit stronger. Next would be polar, covalently bound with hydrogen bonding, right? A little bit stronger. After that, you're starting to get into the bulk solids, where you're going to start having a lot of forces happening. Metallic, then ionic, and then the strongest would be network covalent. So if you want to rank things based on their properties, based on their IMFs, you're going to use this chart. So kind of the steps that you're going to do, you first have to identify the type of IMF you have. You can't just look at a formula and magically know what it's going to be. You have to see what type of IMF it has first, or you're not going to be able to rank anything. Second, you have to put them in order based on your general ranking from that previous slide. The third bullet point here is reminding you of a couple things. If you're trying to rank two things, decide which is stronger, which is weaker, and they only have London forces, then you got to rank based on the largest number of electrons, because remember, the amount of London force increases as you increase the electrons. That's our simplified version, right? The other thing is, if you're trying to rank two things that are only dipole, then you're going to see which has the biggest electronegativity difference between atoms, because that's going to give you the bigger dipole, which will make the stronger dipole force. Okay? So we're going to do an example. I'm going to give you a bunch of compounds. You're going to try to identify what type of force is present, and then you're going to try to rank them from lowest to highest boiling point. Remember that the boiling point will increase as the IMFs increase. So write down these examples, and then we'll start to go through and identify them. So hydrogen is nonpolar, so the only option here would be London dispersion force. Silicon dioxide was one of those special examples you have to memorize. That's a network covalent. Hopefully you would know that copper would just be metallic. We just have a chunk of copper metal sitting there. Carbon monoxide has carbon on one side and oxygen on the other, so that's not an equal distribution of electrons. That oxygen is more electronegative, so this side will be a little bit negative, this side will be a little bit positive. It's not going to have the special criteria for hydrogen bonding, so it's just a plain old dipole. Bromine is also non-polar. It's the same on all sides. So the only force there will be London dispersion forces. Water, if you remember, has lone pairs on the oxygen, which cause it to be bent. That means it ends up polar. It also meets the criteria for hydrogen bonding. We have a hydrogen connected to one of the NOF atoms. The oxygen has lone pairs on it, so that will be a hydrogen bond. The last one tends to throw people because they tend to forget how to tell whether or not something is ionic. Remember, if you have a metal and a nonmetal, a cation and an anion, plus and minus, that's going to be ionic. Remember, not all ionic substances are metals and nonmetals. Most of them are, but the real way to distinguish them is by saying it has a cation and an anion. Remember those polyatomic ions you're supposed to memorize? You can't forget those, or you may miss some of these ionic ones. So for the lowest substance, the lowest boiling point will have the weakest forces. London dispersion are the weakest, but I have two things with London forces. I have hydrogen gas and bromine gas. But if I look at that, I have to remember the larger the molecule, the more London forces it has. That means hydrogen is going to be the lowest, and then bromine gas. Both London forces, but that's how I rank them. Next will be a plain old-fashioned dipole-dipole, then hydrogen bond. At that point, we're kind of crossing over into the bulk solid area. Things start getting much stronger. So now we have metallic. The next strongest would be something that's ionic. And then the strongest thing with the highest IMFs and the highest boiling point would be that network covalent. This time our network covalent was silicon dioxide. So hopefully you can kind of see that I had to identify what they had first, and then I could rank them. All right. On your own, please try to watch this video. It's about geckos. It's a cute little TED Ed video. They have great animations. I don't know if you know anything about geckos, but geckos are well known because they can climb upside down and on surfaces that are very, very smooth. And for a very long time, they had no idea how they did it. They don't have anything sticky on their hands and feet. They don't have little suction cups. They did not understand how they were able to climb the way they did. And I really like showing this video, especially because I went to college at Lewis and Clark, and there was a biology lab that was working on this question. And one of my friends worked in that lab. And so she helped them figure out how geckos were able to climb on things. And so we were able to go look at the geckos, which was kind of fun. So please watch this. It does a great job explaining how geckos use the intermolecular forces that we just learned about in order to do this. All right, everybody. I hope that was helpful. Bye.